In this work, we introduce a physics-inspired cloth simulator that can simulate time-dependent persistent wrinkles. We start the experiments with the on-body garment simulation, which is common in 3D animations. The first experiment simulates a pair of trousers. To compare the persistent wrinkles caused by different deformations, we prepare two different motions, lifting one leg and sitting. The former bends the knee area of the trousers moderately, while the latter results in larger deformations. To test the time dependence, we keep the pose for 500 seconds before putting down the leg. Then, we compare the formed wrinkles with those formed by putting down the leg immediately. Likewise, in the sitting motion, we let the two avatars stand up immediately after sitting down and sit for 500 seconds before standing up respectively. By comparing the left two figures with the right two, we can observe that the persistent wrinkles formed by lifting the leg is milder than those formed by sitting. By comparing the two figures on the left or the two figures on the right, we can see that keeping either pose for 500 seconds makes the persistent wrinkles firmer and sharper. Thus, our simulator can vividly simulate persistent wrinkles on garments caused by different motions and different durations of the deformations. The photos show the real-world counterparts. Lifting a leg and immediately putting it down only introduce very mild wrinkles, while keeping the pose for 15 minutes makes the formed wrinkles firmer. These can demonstrate our simulations are visually plausible and convincing. Also, the formed wrinkles become sharp after sitting, and sitting for 15 minutes makes the wrinkles look even sharper. Cloth materials also determine persistent wrinkles. Cotton is soft and likely to form small persistent wrinkles, while denim is much stiffer and more likely to have larger persistent wrinkles, whereas polyester resists to persistent wrinkles. We simulate 3 pairs of trousers made from these materials and then compare the formed persistent wrinkles caused by the sitting motion. We also keep the avatar sitting for 500 seconds to simulate how the persistent wrinkles change with the duration of the deformations. The figures show that cotton and denim trousers have more persistent wrinkles than polyester ones. In addition, keeping sitting for 500 seconds makes the formed wrinkles on the cotton and denim trousers more obvious. We also simulate the persistent wrinkles on a t-shirt caused by rotating the top body and bending arms. Similarly, keeping the pose for 500 seconds let the formed wrinkles deeper. To more clearly evaluate our simulator, we also conduct simulations in more controlled scenarios with using simple cloth samples. We let a rectangular wrinkleless cloth sample fall into a cylindrical obstacle. The cloth is folded moderately due to its self-weight, and the major reason for the persistent wrinkles is the internal friction. The wrinkles on the right cloth look more obvious than those on the left because the right cloth is held and kept in the folded state for 500 seconds before lifting. Thus, our simulator can effectively simulate time-dependent persistent wrinkles in moderate deformations. To deform the cloth sample more extremely, we continuously let it fall onto the floor and press it to incur more persistent wrinkles caused by plasticity. Similarly, we keep pressing the cloth for 500 seconds before lifting it up to test time dependence. The results show that, first, compressing the cloth incurs sharper wrinkles, and second, compressing the cloths for 500 seconds make the wrinkles even more obvious. Then, we compare with the existing physics-inspired cloth simulators. Compared with a cloth simulator integrating the hardening plastic model, our simulator not only can simulate more moderate wrinkles caused by internal friction, but can also simulate wrinkles time dependence. We then compare with doll friction model, and it cannot simulate cloth wrinkles time dependence either. Moreover, due to the lack of stick friction, we need frequently slow down cloth motion to prevent the newly formed wrinkles from disappearing. Last but not least, We conduct ablation studies to further testing our friction model, plastic model, and simulator. We switch off our plastic model to demonstrate our friction model can simulate time-dependent persistent wrinkles by itself. As shown in the video, the wrinkle can be formed by a moderate bending and becomes more obvious after in the folded state for 500 seconds. In addition, the wrinkle can be easily flattened again for dragging a cloth. Then, we switch off our friction model to simulate the persistent wrinkles governed by our plastic model. The videos demonstrate our plastic model can independently simulate time-dependent persistent wrinkles as well. However, the cloth needs to be bent more largely to form the wrinkle, and the formed wrinkles cannot be easily flattened by dragging. Next, we twist cylindrical cloths with using different time-step sizes to test if the simulated wrinkles are time-step size invariant. The videos show that the persistent wrinkles do not vary when using 3 different time-step sizes. Finally, we twist cylindrical cloths made from cotton, polyester, and denim, and then compare the formed wrinkles. Thank you for watching this video.